refuse to load. I know, because I have many technical difficulties. Okay, so why don't you get notes out for me? So we are going to talk about trigonometry. Can you stop talking, please? So the word trigonometry is from Greek. And what does the tri part mean? 3. So it's triangle, and the nometry part is measurement. So trigonometry, when it was invented by the Greeks, now you're talking you're talking about BC. Like that's when they started dealing with stuff like Pythagoras and the Pythagorean theorem. He's BC, or else really small numbers, AD. So this has been around a long time. And when they first started into trigonometry, it was for things like ship navigation, surveying. Do you guys know what that is? That's when you'll see them road crews surveying every once in a while. There's always a guy in the middle of the road with like a tripod thing, and he's looking like they survey for roads. They survey if you ever go out and buy a piece of property, they have to survey to see if the property lines are in the correct place. So they used it for navigation and shipping, and surveying. There was one more that I can't remember right now. In the 17th century, when they started coming around with calculus and things like that, which is when calculus was invented, and physical science type things, there was a whole lot more applications of trigonometry. So all of the waves, like sound waves and light waves, stuff that has to do with chemistry and subatomic particle behavior, things like that. Like there's a whole different array of things. So the chapter that we have will cross over into a lot of different areas. Of all of the things that I think in geometry are useful, Pythagorean theorem and the stuff that we're going to talk about today and tomorrow. Actually, things I've used in my real life outside of this classroom. Because you build a deck, you build anything out of wood, and you're going to have to do some measuring, and you're going to have to deal with some things. Okay? So just some thoughts for you there. So we're talking about right triangle trigonometry. So I would like to remind you that in geometry class, we talk about, we name our triangles based on their angles. So in geometry class, we have right triangles, which are triangles that have a right angle. Go figure. There are also things called acute triangles. Acute triangles are ones where all of their angles are less than 90 degrees. They're small. Obtuse triangle is one where that has one big angle. But there's also things like isosceles. Do you remember what isosceles is?
It's like a normal triangle.
Two sides are two angles. Two sides, so in terms of angles, an isosceles triangle has two angles that are the same. And then there's equiangular triangle, which are all the same. Hello, equiangular, that makes sense. Sounds like equal angles. So triangles can be named based on their angles. Trigonometry as itself, as opposed to just plain old geometry, deals specifically with right triangles. So there's there's a couple things you need to know. First of all, that is this. I'll make it bigger for you. That's that. That is a variable. It's a Greek letter. Okay, and it is the variable theta. It's the third Greek letter, alpha, beta, theta. It's the one that math people decided they were going to use for angles. Okay, so that a lot of times it's just a variable that you will see, and it represents angles. Okay, so don't freak out on it. It's just a variable. Now we talk about three different ways to talk about sides of a triangle. So first of all, I said to you that these guys are legs. So the ones that touch the right angle are legs, and the one that is opposite of the right angle is the hypotenuse. Jack asked if that sounded funny. Jack asked if the hypotenuse was always the longest one. And that is true, but sometimes if they're close or if it's sitting on its hypotenuse, it's hard to tell. So the hypotenuse is always across from the right angle. This guy is called the opposite side. Okay, he's opposite of theta. It's all related to where is the angle. So this side is opposite of the angle. This is, by the way, flat out geometry review. I know it's been a while though. Okay, so opposite means like if you look at the two rays that make the angle, at the end of those two rays is the opposite side, right? It opens up and encloses the opposite side. This guy is the adjacent side. Okay, adjacent means next to. So this is adjacent. Sometimes people are like, but wait, the hypotenuse touches the theta also. Adjacent touches theta. Okay, it's next to the angle. The hypotenuse is the hypotenuse, so it's not adjacent. Opposite and adjacent are how we describe legs. Hypotenuse is hypotenuse. So just to make sure that you are with me, you do not even have to write this down. Okay, let's say we've got A, B, and C. And let's slap theta up there. Okay, you do not have to write this down. What side is opposite of theta? You guys agree? Okay. C is opposite of theta. Joe, because if you drew a line out of theta, it's going to hit C. So it's opposite. What's the hypotenuse? B. And what is A? A is adjacent. Okay, so hypotenuse, opposite, and adjacent. Now, those are important because of these things. Okay, so on this paper, we have this first bit is what we're going to fill out right now. So we know this is an acronym, SOHCAHTOA. It doesn't really mean anything. It's just a way to remember what these definitions are. So the sine of theta, which is S, is defined as the opposite over the hypotenuse. So these guys are fractions. So SOH is sine, opposite hypotenuse. You have to remember that they're divided. So sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. And tangent is opposite over adjacent. Why are they called that? I don't know. Couldn't tell you. So you do not have to write this down. I just want you to listen. So in geometry, there is a thing called similar triangles, which we're not even going to get into. Like, do you guys remember doing proofs and all that jazz? This is my best go at this, okay? So a similar triangle is one where they have a similar angle and then their sides are related to each other by some type of a scale factor. You don't have to know that. But the point is, you can see that this guy is 1.5. This guy is 1.5 times this one. This one is 2 times this one. They're similar. They have the same angle. They're supposed to be all looking exactly the same, but I can't draw. So that's the way it is. What I would like you to do is to find the sine of 30 degrees. This is 30 degrees. So if you can see, the sine of 30 is sine, by definition, is opposite over a hypotenuse. So opposite over hypotenuse in this triangle is what? 1/2. It's 2 over 4. Okay. This triangle, which is similar, what's his sine opposite over hypotenuse? 3 over 6. And in this triangle, which is also similar, what's the sine? 4 over 8. Now, because of the way triangle similarity works, these are all equal. What is that equal to? 1/2. And in your calculator, you will find that your calculator knows that the sine of 30 is 1/2. So let me show you how to do this. Go to mode on your calculator, which is here. Okay. It should be about the third line down. I have different size font than you because this is old. But you should have normal, float. But next thing you should have is radian and degree. You want to be in degree mode. Okay, so make sure you hit enter so that it does that. And then you can quit. Okay, so second mode. Now type in sine of 30 on your calculator. The sine of 30 is 1/2 because in every triangle with a 30 degree, every right triangle with a 30 degree angle, its sides have the same relationship. And so all of the things that we talk about, your calculator knows the values of them. Like it must be a program in there or something because you can give it like some crazy decimal and it knows the sign of that. I do not program calculators, so I don't know how it knows it. It just does. So we will use the fact that these are all constants. We use that to solve problems later. Okay, so for now, you don't have to worry about it. I'm just letting you know. Sine of 30 is always 1/2. Sine of 45 is always 0.707. So they always are the same. What I would like you to do, let's throw theta down there and let's go x, y, and z. I would like you to find the sine of theta, the cosine of theta, and the tangent of theta. Just to make sure you know what you're up to. This, by the way, is the first question on chapter 4 test is like this. Just in case you wondered. First question on the chapter 4 test. Probably on the quiz that will not be this semester either. Okay, what is the sine of theta? Is sine of theta is y over z because it's opposite. This is opposite or across from theta, y. And then over the hypotenuse, which is z, because that's the hypotenuse. What's the cosine of theta? Yep, adjacent, which is next door over the hypotenuse. Oh, x over z. And then what's the tangent? Yep, y over x. So opposite over adjacent. So y over x. Guys, it seems like it's goofy to spend time on that with letters, but for what we're doing, you have to be able to know what is opposite and adjacent. Okay, otherwise you're going to be out of luck real bad. Now, these are the big three. Everybody was happy with these until some Danish guy in the 1500s came up with the other ones. So there are actually 3 more. We do not use them very often for solving story problems because these are the big 3. Also, if you notice, your calculator has sine, cosine, and tangent on it right across the middle here. It does not have the other 3. So don't worry about it, pretty much. This CSC stands for cosecant. Cosecant. And cosecant is hypotenuse over opposite. Jack, you should be writing. Okay, hypotenuse over opposite. This SEC is secant. Which is hypotenuse over adjacent. Anybody got a guess on the COT?
Adjacent over opposite.
Oh, it's adjacent over opposite, and it's cotangent. And it is adjacent over opposite. Now, here's what I'd like to say. The only time I use those three, I don't use those in my real life. The only time we use those is when we're doing mathy things in math class. But I do like the completeness because when you add those three, if you notice, everything has a co. So sine has a cosine, tangent has a cotangent, secant has a cosecant. Okay? I just like the completeness of it, which is neither here nor there. But I would like to know if you see the relationship. Yeah, I know that Joe caught it, and Ace just did this business. These are reciprocals. So if you look at sine is opposite over hypotenuse. Cosecant next door is just reverse. It's just upside down. Okay. So once you know that they're reciprocals, it becomes a lot easier to use them. So what I would like from you now, I'll give you another triangle here. I don't want that one. Let's go with this one. I know. Okay, I would like you to find all six. Let's go with this theta. Okay, so sine, cosine, tangent, cosecant, secant, cotangent. Okay, so you're finding all six of those for that triangle right there, please. Okay, what's a sine? What's the sine? M over N. So this is an example when this, I know I'm not picking on Jack, sounds like I'm not. When he was like, hey, the hypotenuse is the longest, sometimes people get confused because they feel like it can never be the bottom, the base. In this case, the hypotenuse is the bottom of it because it's across from the right angle. So you just got to watch that little bit of sneakiness. What is the cosine of theta? Yep, P over N. What's the tangent? Yep, M over P. So opposite, adjacent, M over P. Okay, now, you guys, these three are easy. What's the cosecant? Yeah, n over m, because it's just it's the reciprocal of this guy. Secant is n over p, and cotangent is p over m. Okay, there you go. So that's the idea. We will get into stuff with the other three, but honestly, for pre-exam stuff, it'll only be the sine, cosine, and tangent. So one of the things that you'll see is you'll see questions that look like this. Oh, poo. We'll say find exact values of all six. I'm not listing them all. Okay, so when you see the words exact values, okay, that means that you need to make sure that you are not using decimals. And it really means reduced fractions only. Okay, reduced fractions only. So exact values. So I would like you to find all six, please. Okay, sine, cosine, tangent, cosecant, secant, cotangent. Ooh, great question. So, no, well, that's the short answer. No, thank you. And we'll talk about that in a second. Yep, just like that.
Because you have to find hypotenuse first.
Yep. Okay, so somebody said to me, you have to find the hypotenuse first, which is true indeed. So this is why we reviewed Pythagorean theorem at the beginning of the hour on our warm-up. Okay, so remember, Pythagorean theorem is if you know two sides of any right triangle and you need the third. So in this case, you have to do 3 squared plus 4 squared equals the hypotenuse squared. What is the hypotenuse? How long is it? It's 5. Okay, so once you know that it is 5, your life becomes easier, I guess. What's or possible to do this? What's the sine of theta? Yep, 4 over 5. What's the cosine of theta? Yep. Tangent?
4 over 3.
Okay, so I'm going to pause a second and say this. Ace asked about mixed numbers. Don't ever use mixed numbers. Ever, 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 ever in this class. Honestly, you're in this class, so it doesn't make sense. Like once you hit algebra, people should not be using mixed numbers anymore. They teach them in elementary school, I think, because it makes sense for a little kid to add, right? Like if a little kid was going to add, 3 halves plus 3 halves, there's no little kid in the world that would be like, oh, but if you said to a kid, hey, you're going to do 1.5 and 1.5, they can be like, oh, that's 2, and then I have a 1/2, and that's 3. They can do that. They can't do this, which is how we should be doing it. So they're taught in elementary school because of little kid reasoning levels, basically. That's what I got. So all that to say, we don't use them. Okay. We don't ever want to use mixed numbers. They're really just not mathematically appropriate. So these are called improper fractions, which sounds bad, but actually want everything improper if it's possible, right? If it's improper over mixed numbers, I guess we'll go that way. Okay. Anyway, what's the cosecant? Yep, 5/4. Secant, 5/3. And cotangent, 3/4. Like I said, once you know the big ones, you just got to remember that those are reciprocals across from them on your paper. Like this is reciprocal. Makes life easy. Now, and you share a shortcut with you. Take it or leave it. I don't care what you do with this. Okay. There is a thing in math, this thing that makes math teachers' lives a little bit easier. Pythagorean triples are a set of three numbers that works nicely in the Pythagorean theorem without decimals, right? So 3, 4, 5 that I just gave you, that's a Pythagorean triple because 3 squared plus 4 squared equals 5 squared. It works in the Pythagorean theorem and there are no decimals. Okay, so the only reason I'm telling you that, well, let me say this. Let me pause. There are infinitely many Pythagorean triples. The reason there are several base ones, and then I can take any multiple of this. I can double that. So 6, 8, 10, that's a Pythagorean triple. 30, 40, 50, that's a Pythagorean triple because I can multiply them by 10. Those ones aren't going to help you out a whole lot, but I will tell you that 3, 4, 5 gets used an awful lot, and it will save you some time if you can remember that 3 and 4 go with 5. Okay, the other one that is the most commonly used one is 5, 12, 13. Okay, 5, 12, and 13 is a Pythagorean triple. Where if you have two legs and it's 12, it will save you time if you're like, well, I know the hypotenuse is 13. If you don't remember, it's fine because the Pythagorean theorem will always work. Case in point, our warm-up that we did today was double that. You had 10 and 24, and the answer was 26 because that's double that. 10, 24, 26. There are other base ones that I don't know as well, like something 15 and 17, I think, might be 8, 15, and 17. I don't know. But anyway, these are most commonly used. Okay, most commonly used. Now, what I'd like from you is, I am not in the right book. Yikes, just a second. I was going to give you a calculus problem to do, and that would not go well. I would like you to not do that problem. Okay, why don't you try this one, please? Oops, that's my theta. It's just sloppy. Okay, same thing. First of all, I would like you to notice this is not a Pythagorean triple because it's 5 and 2. So, no love. What I would like you to, we're going to do this one together because I don't want you to do anything foolish. I'd like you to find the missing side. Please and thank you. What'd you get?
I don't know.
Oh, you were locked in. That's what you told Sven.
That's gonna tell me anything.
Yeah, I think you're making it a decimal.
Okay, so you have a problem because it's a decimal, right? So if you're going to do this, I'm going to call this A for the sake of whatever. So A squared plus 2 squared equals 5 squared. So this is A squared 4, 25. So you get A squared is equal to what? 21. So A is equal to the square root of 21. you leave him, if we're doing exact values, you leave him as the square root of 21. Okay, now go ahead and do the rest of them. So we're finding all 6. So sine, cosine, tangent, cosecant, secant, cotangent. Okay, what is the sine of theta? 2 over 5. Cosine? Square root of 21 over 5. Tangent? Okay. Secant? 5 over 2. Cosecant? Yep, and cotangent. Okay, now tomorrow when we come in, these are not all proper. And we'll talk about why and what we have to do about that. Well, that's a problem for tomorrow.